China just spent over $1 billion on glass. Read that line again. Not on hyper-advanced transistors, not on the multi-million-dollar lithography machines used to print them, on glass. On its surface, that sounds like a bizarre, almost counterintuitive allocation of capital. But that single, massive bet may have just exposed the single greatest vulnerability sitting underneath every advanced artificial intelligence processor on Earth today. It is a fundamental weakness that almost nobody outside of elite semiconductor engineering circles is actively discussing. Here is what makes this the absolute most fascinating narrative unfolding in technology right now. This story isn't actually about what China built. It's about what China understood while the rest of the global technology sector was looking somewhere else. For the last half-decade, the global conversation around microchips has revolved around a single, relentless obsession: shrinking transistors. Who can etch the smallest features into silicon? Who can pack more logic gates onto a square millimeter of material? The entire semiconductor industry, alongside trillions of dollars in government policy and national security strategy, has been organized around that single race. At the very center of that global effort sits a single Dutch manufacturing giant named ASML. Their extreme ultraviolet lithography machines are effectively the only tools on the planet capable of printing the smallest, most advanced logic structures onto silicon wafers. Each system weighs as much as 2 fully loaded city buses, costs upwards of $200 million to $350 million, and relies on tens of thousands of hyper-customized parts supplied by a fragile, highly exclusive global network. They represent, without hyperbole, some of the most complex engineering achievements in human history. Because of this, a simple, dogmatic logic took hold across Western technology hubs. Control the lithography, control the future. The assumption was clean, linear, and persuasive. If a country or company cannot access ASML's top-tier lithography tools, it cannot manufacture state-of-the-art transistors. And if it cannot build those transistors, it can never lead the world in artificial intelligence. It was a perfect argument, except for one massive, overlooked blind spot. That logic only holds if shrinking individual silicon transistors remains the only viable pathway to delivering more computing power. China quietly, systematically, and very deliberately decided that it isn't. Think of it like a global auto race, where one dominating team has successfully monopolized the world's supply of high-performance racing tires. Most competing teams would spend a decade trying to clone or reverse engineer that specific tire compound. China took a step back, examined the track itself, and set out to build a completely new vehicle engineered for a surface those original tires could never run on. That surface is called advanced packaging, and the vehicle is glass. To understand why this strategy is so disruptive, you have to realize a basic truth about modern hardware. The most capable AI processors deployed today are no longer monolithic, single pieces of silicon. They are massive, interconnected multi-chip assemblies, often called chiplets. Dozens of separate, highly specialized mini-chips, ranging from memory blocks to compute cores, are wired together on a shared base and engineered to function as a single, unified processing engine. That shared platform underneath all these components is known as the substrate. The substrate serves as the physical and electrical bedrock of the entire chip package. It routes electrical signals between individual chiplets, delivers power to millions of tiny points, and acts as the primary thermal conduit to dissipate the enormous amounts of heat generated during high-performance compute tasks. If the individual chiplets are high-rise skyscrapers, the substrate is the bedrock foundation and subterranean infrastructure holding the entire city together. Right now, almost the entire global tech economy relies on foundations made of organic material, essentially a hyper-engineered, highly complex form of industrial plastic resin reinforced with woven fiberglass. This is where the entire narrative pivots. China is not attempting to outshrink Western silicon fabricators at their own game. China is trying to replace the physical floor that everyone else's chips are standing on. While the rest of the global tech sector was heavily guarding one front door, China quietly walked around to the side of the building. To grasp why that move carries such staggering strategic leverage, You have to look closely at why those traditional plastic foundations are beginning to fail at the worst possible moment in the history of modern computing. Here is an inconvenient reality that hardware manufacturers don't emphasize in their promotional keynotes. The world's most sophisticated AI processors, the engines training massive neural networks, are held together by advanced plastic. Organic substrate formulations have served the tech industry brilliantly for decades. They were cheap, flexible, and perfectly suited for an era when microprocessors were small, relatively cool, and far less dense than today's hardware. That era has effectively ended. The flagship processors driving the current AI revolution are massive physical entities. A modern multi-chip package can easily exceed 8,000 square millimeters in surface area. Picture placing 4 standard playing cards side by side. That gives you a sense of the physical footprint these packages now occupy. Across that expansive area sit billions of microscopic electrical interconnects, all firing simultaneously, drawing massive currents, producing staggering heat, and depending utterly on one absolute condition: that the underlying substrate remains perfectly, dimensionally immobile. Here is the fatal flaw. Organic materials expand and contract significantly when exposed to thermal flux. Every time an AI processor powers up, handles a heavy computational load, heats up to extreme temperatures, and cools back down, the plastic foundation beneath it physically shifts. We aren't talking about movement you can see with the naked eye. These dimensional shifts are measured in parts per million. But when you are dealing with interconnects packed tightly at microscopic scales, a variance measured in parts per million is not a minor rounding error. It is a slow-motion structural failure. As the organic base expands and warps under heat, the microscopic connection pads, many far thinner than a strand of human hair, begin to experience physical strain. Over thousands of thermal cycles, those pristine electrical connections degrade, experience signal degradation, or fracture completely. Imagine a massive, long-span suspension bridge during a severe heat wave. The individual steel cables don't snap instantly. They expand slightly under the thermal load. But if every structural calculation in the bridge's blueprint assumed zero movement, that minor expansion is enough to throw the entire structural architecture out of tolerance. That exact phenomenon is taking place inside advanced AI clusters right now. It isn't an explosive failure. It's a quiet, progressive mechanical drift that hardware design teams can measure, but struggle to eliminate, because the underlying plastic material is deeply embedded across 50 years of global supply chains and manufacturing lines. This vulnerability was manageable when chip packages were small and workloads were modest. But the entire trajectory of future computing demands larger packages, denser interconnect architectures, higher power draws, and significantly greater thermal output. Every variable that causes organic plastic substrates to degrade is worsening at the exact same time. The core question was never whether plastic substrates would hit an absolute physical limit. The real question was, which nation or enterprise would have a fully scalable replacement engineered and ready when they finally did. The ideal replacement material is something you likely interact with in your daily life, far away from clean rooms or supercomputing clusters: borosilicate glass. If you take a high-durability glass baking dish out of a 400-degree oven and place it onto a cold surface, it doesn't shatter or warp. It maintains its structural form. That resilience isn't accidental. It is a fundamental physical property of the material's molecular geometry. Now, take that exact material science principle, compress it down to a sheet thinner than a human fingernail, engineer its surface flat to sub-micron tolerances, and you begin to understand what semiconductor-grade glass substrates are designed to achieve. This is not the glass used in standard kitchenware or smartphone displays. It is a purpose-engineered, hyper-pure material built to overcome every inherent physical limitation of organic resins. First, consider structural and thermal stability. Where organic plastic warps, bends, and expands under thermal stress, semiconductor-grade glass maintains its physical geometry with remarkable rigidity. The intricate electrical paths printed onto its surface stay precisely where they were laid down, regardless of whether the processor is idling or operating under maximum compute workloads. There is no physical creep, no thermal drift, and no mechanical stress pulling delicate chiplets out of alignment. Second, there is radical interconnect density. Because organic materials exhibit microscopic surface roughness and mechanical instability, there is an absolute physical limit to how closely you can pack copper traces before signal interference occurs or manufacturing yields plummet. Glass, by contrast, can be made almost perfectly smooth. As a direct result, glass substrates can support up to 10 times the interconnect density of the absolute best organic substrates available today. Third, look at signal integrity. Organic substrates naturally absorb, distort, and scatter high-frequency electrical signals as they travel through the medium. Glass does not. Electrical signals passing through a glass substrate experience significantly lower attenuation and crosstalk. Signals arrive faster, cleaner, and with drastically reduced power loss, enabling distinct chiplets to communicate across a large substrate as if they were sitting on the exact same piece of native silicon. The true breakthrough, however, is not any single one of these characteristics in isolation. It is what they enable when combined. With a foundation that refuses to warp, accommodates 10 times more connections, and maintains pristine signal quality across wide physical distances, chip designers can break past current physical limitations. They can build massive, highly integrated package architectures that plastic could never dream of supporting. It is not just about producing a slightly better chip. It is about deploying a superior physical foundation that elevates the performance ceiling of every chip mounted upon it. If glass substrates offer such decisive performance advantages, why hasn't the entire global semiconductor supply chain converted to them already? Because manufacturing semiconductor-grade glass at scale is one of the most brutally difficult engineering challenges in modern industrial science. To visualize the problem, imagine taking a common plastic drinking straw and scaling its diameter down until it is significantly thinner than a single strand of human hair. Now imagine trying to drill tens of thousands of those perfectly straight, completely parallel, flawlessly smooth holes through an ultra-thin sheet of rigid glass, without cracking the panel, and without causing microscopic internal stress fractures that might only cause the chip to fail months later inside a data center. Now, imagine repeating that process millions of times per day, with precision yields high enough to make the unit economics commercially viable. This is known as the through-glass via problem, and it is the primary reason why glass substrate technology remained a theoretical ideal for years rather than a commercial reality. A via is simply a vertical electrical conduit, a tiny hole drilled through a substrate layer so that electrical signals and power can travel cleanly between different levels of the package. In organic plastic, drilling vias is relatively forgiving. The material is pliable, absorbs mechanical vibration, and can be easily processed with standard laser tools. In glass, there is zero structural forgiveness. Glass is rigid and brittle. It severely punishes any physical imprecision with microfractures that propagate silently through the substrate until the entire unit structurally fails. And drilling the holes is only the first hurdle. Once those microscopic vias are created, they must be filled cleanly with conductive copper and bonded securely to the glass walls. Here, physics presents another massive hurdle. Glass and copper expand at vastly different rates when exposed to heat. If the interface between the copper pillar and the glass wall is not engineered at a molecular level, repeated heating and cooling cycles will cause the copper to detach from the glass wall. The via may look structurally sound on the outside, but the internal electrical connection is severed. Then there is the issue of manufacturing yield, the percentage of finished substrates that emerge from the production line completely defect-free. Early experimental glass packaging lines suffered from yields so low that the cost per usable unit was economically absurd. You cannot build a global hardware ecosystem on a material process that fails more often than it succeeds. Finally, there is the requirement of surface flatness. A glass substrate panel must remain flat within tolerances measured in single-digit micrometers across its entire surface area. For context, a single micrometer is roughly 1/70th the diameter of a human hair. Maintaining that level of absolute flatness while subjecting the glass to extreme heat, chemical etching, and rapid mechanical handling proved to be a multi-decade engineering puzzle. This combination of extreme process complexity, punishing initial yields, multi-year customer validation timelines, and astronomical capital costs is precisely why most global chipmakers viewed glass substrates as a long-term research initiative for the late 2030s rather than an immediate industrial imperative. China looked at those exact same barriers and saw an entirely different scenario, an unfortified strategic moat it could cross before anyone else realized a bridge was being built. The common consensus in many Western policy hubs is that China's semiconductor sector is perpetually playing catch-up, throwing massive state subsidies at established technologies and hoping to compress decades of Western domain expertise into a few short years. In the realm of glass substrates, that assumption is entirely inaccurate. China is not starting from zero. It is pivoting existing industrial capacity. Consider a Chinese industrial titan that few outside the display electronics sector pay attention to: BOE Technology Group. Inside the display industry, BOE is a massive force. It is one of the world's largest producers of flat panel display glass, the high-precision glass sheets that form the basis of modern televisions, computer monitors, tablets, and mobile devices. BOE's advanced manufacturing facilities are vast, with single production campuses spanning floor space equivalent to major international airports. To dominate the global flat panel display market, BOE spent over a decade perfecting the precise manufacturing discipline required to handle ultra-thin, large-format glass panels at massive scale. Think carefully about what display panel manufacturing actually requires: handling ultra-thin glass sheets at high line speeds without breakage, controlling surface flatness and purity across wide surface areas, maintaining precise thermal control throughout heavy processing steps, and managing high-volume yield optimization, where single-micron defects ruin entire batches. The end product is different, and the specific fabrication equipment varies, but the core industrial muscle memory, process engineering philosophy, and high-volume glass management infrastructure are directly transferable. This detail changes the entire perspective. The glass substrate bottleneck is no longer purely a theoretical material science problem. The underlying physics are well understood. The true challenge is advanced high-volume manufacturing engineering, handling ultra-thin, brittle substrates with absolute precision, high yield, and sustainable unit economics. And that happens to be the exact domain expertise BOE and its supporting supply chains have been refining at scale for years. BOE is not acting in isolation. A network of specialized Chinese technology firms, equipment suppliers, and material fabricators have been aggressively targeting the through-glass via challenge, refining precision laser drilling, copper metallization, and stress mitigation protocols with substantial capital backing. This massive effort is funded directly by China's National Integrated Circuit Industry Investment Fund, alongside regional state venture capital. It represents a coordinated national industrial initiative designed to convert a high-risk technical frontier into a dominant commercial supply chain. When you aggregate direct capital investments from China's state funds, local municipal development vehicles, and joint corporate expenditures since 2023, the total capital directed explicitly toward glass substrate technology easily clears $1 billion. That capital was not allocated to fund basic academic research or publish white papers. It was directed straight into scaling pilot lines, optimizing industrial yields, building specialized lithography and TGV drilling equipment, and establishing the raw material supply networks needed for commercial-scale output. Investment at that magnitude, targeted at a highly specific structural bottleneck, only occurs when a country makes a high-level strategic assessment that this specific packaging layer will dictate the future of high-performance hardware, and that early industrial dominance is mandatory. China appears to have made that strategic bet around 2022, at the exact moment the global tech narrative was completely focused on lithography access and ASML export controls. And that initial $1 billion is just the foundation. A single commercial-scale glass substrate fab can cost anywhere from $500 million to over $1 billion to construct and fully qualify. But in China's state-directed capital framework, Once a technology's strategic value is proven, the capital pipelines open wide. This brings us to why this race is so extraordinarily time-sensitive. In semiconductor manufacturing, the first-mover advantage creates a compounding moat that is nearly impossible for latecomers to overcome. This advantage isn't just about owning advanced machinery. It is about the vast, unpatentable domain knowledge accumulated on a live production line over years of continuous operation. That process knowledge cannot be easily downloaded, reverse-engineered, or acquired through academic papers. It lives in the operational experience of process engineers, in customized equipment recipes, and in production teams that have analyzed tens of thousands of real-world yield failures and systematically eliminated them. The first entity to reach stable, high-yield volume production captures that knowledge moat first. Furthermore, once an advanced chip designer designs, validates, and qualifies an AI processor package on a specific manufacturer's substrate process, they are locked in. Requalifying a complex AI chip package on a different vendor's process line costs tens of millions of dollars, takes 2 to 3 years of validation, and introduces massive operational risks that tech companies are extremely hesitant to take. This exact economic dynamic is what made Taiwan Semiconductor Manufacturing Company the central player in the global tech economy. TSMC did not secure its position simply by having access to exclusive tools. It won by reaching high-volume production first, learning faster than any competitor could follow, and locking in global chip designers whose product roadmaps became completely reliant on TSMC's manufacturing generations. China carefully analyzed that dynamic and is now actively attempting to recreate those exact market conditions within the substrate space, a domain the rest of the world neglected to secure. In standard hardware cycles, if a competitor falls behind, they can usually observe the market leader, invest heavily, and gradually bridge the performance gap over time. It is expensive and difficult, but entirely doable. The glass substrate transition may not offer that luxury. The advantage being built is not merely a transient tech lead, it is a deeply entrenched, compounding manufacturing advantage. The moment a vendor secures reliable, high-yield glass substrate manufacturing, every panel that rolls off that line refines the process further. The major cloud computing providers and AI hardware developers that qualify their next-generation architectures on that glass foundation will build their future product roadmaps around those precise physical metrics. At that stage, switching suppliers requires a complete, ground-up redesign of the entire processor architecture. That is not a temporary vendor relationship. It is a long-term structural dependency that can shape the balance of technological power for decades. This reality explains why the world's premier semiconductor leaders, Intel, Samsung, TSMC, and specialty glass giant Corning, are suddenly accelerating their own internal glass substrate roadmaps at a pace none of them originally anticipated. Intel, which holds some of the earliest structural patents in glass substrate packaging, has aggressive plans to bring glass substrates to market. Samsung has set up dedicated advanced packaging pilot lines to accelerate its timeline. TSMC has ramped up its internal research allocations, focused on glass-based advanced packaging substrates. Corning is racing to lock down the foundational supply of semiconductor-grade raw glass. A technology that much of the global tech industry once categorized as a distant, theoretical concept for the late 2030s has suddenly transformed into an urgent industrial priority. When you zoom out from the individual engineering details, the broader reality becomes undeniable. The next era of advanced computing may not be decided purely by who prints the smallest transistor on silicon. It may very well be decided by who controls the physical foundation those transistors sit on. Every artificial intelligence model, every hyperscale data center, and every autonomous system built over the coming decade will rely on complex chiplet assemblies. And those assemblies will require a stable physical foundation to operate at maximum efficiency. Whoever masters that base layer and locks in the surrounding global supply chain will hold a strategic position that is extraordinarily difficult to disrupt. That is what a billion-dollar bet on glass really buys. Not just a material innovation, but structural control over the future of hardware.